welcome to chapter 2. So we will discuss the basics of computer architecture, and these basics are from the point of view of the operating system. So we'll have 4 sections here. The first is course, registers and interrupts, but again we'll focus on the OS specific part. It's not meant to be a generic introduction to all computer architecture concepts. So for that, an architecture course is there, but this will only look at privileged instructions, privileged registers, things that affect the functioning of the OS. Given that the x86 assembly part plays a very important role here, we will spend some time understanding x86 assembly. Virtual memory is always a tricky concept, but it is an integral concept for operating systems. So it doesn't hurt us taking a second look at it, especially from the point of view of Linux. And I/O. So I/O is again an issue which we need to look at several times in different levels of detail. So modern chip is a reasonably complex beast, but the interface to software hasn't really changed over the years. So a lot of the complexity has been very nicely hidden by hardware. So whatever was the interface to the OS, that has more or less remained the same. Of course, with time, some complexity has been added, but that complexity is not a lot. So you have your cores, caches and main memory. 4 to 64 cores are common, so it's common to have an octa-core mobile phone, for instance. And you have a hierarchy of caches, first level, second level, third level. Often you may have a fourth level as well, which may be off chip. And then you have an off chip main memory. So all of this, typically the cache structure is hierarchical in the sense that all the addresses in the level 1 will also be there in level 2. Of course, the data may be fresher in level 1. So on and so forth for level 2 and level 3 and the main memory. The main memory is kind of like a superset of the address space insofar as the caches and main memory are concerned. But later on we'll look at swap space, which further extends the what is called the physical address space. Physical address space is all the locations in that can actually be physically accessed based on an address. That is the physical address space. It is not the view that programs or the compiler see, it is the view that the hardware sees. So for the hardware, there is a single address space. An address is basically nothing but a 32 or 64-bit number. If it's a 32-bit machine, a memory address is 32 bits. If it's a 64-bit machine, a memory address is 64 bits, but all 64 may not be used. You may say that I will only use 48 bits and the upper 16 bits will all be 0. That's fair because 64 bits is a lot. So 48 bits is also a lot, right? So 48 bits is 256 terabytes. Nobody has that kind of memory. At least not as of now, unless there is some radically new memory technology per node. But of course, if you combine a bunch of nodes and so on, you can. So that is a possibility. Nonetheless, the physical address space for the hardware is only a single one. So registers, we all know they are named storage locations and they number from 8 to 32. So x86 has 8, x86 64-bit variant has 16, RISC-V has 32. So that we know. And normally RISC ISAs have more registers because they don't have memory operands or that many memory operands in their instructions. So they use more registers, and CISC or ISAs use fewer registers. So RISC machines, as you can see over here, they would first load a memory value and then work on it, as opposed to CISC machines that will directly work on a memory value. Right, so that is why RISC machines also need more registers as opposed to CISC. So this we have seen, and this is covered in a regular computer architecture class. So what we want to look at here is something beyond general purpose registers. So general purpose registers are the ones that you use to write normal programs. So these are the registers which can be used by all programs, right? This is a general purpose register. But what we are more interested in are the privileged registers, which a normal program cannot see, or even if it can see, it is not allowed to use. So which are registers over and above, beyond this set. So beyond this set of 8 or 16, these registers are kind of a separate set. They can only be used in certain processor modes, so the OS can use them. The virtual machine monitor, known as the hypervisor, whose job is to actually monitor the guest operating systems. In a certain sense, that's like an OS only. That can. And so these are the privileged software entities. They can access these registers, but your normal programs cannot. So what are these registers for? What do they do? So, well, they do a bunch of things. The first is that we have seen registers in our computer architecture course when we were writing an interrupt handler. So there we had a very primordial problem. The problem was that I want to collect the values of all my registers. Correct? So let us say that I have 16 registers and I want to do a snapshot. I want to collect the value of all 16. Okay. Now the question is, how do I collect? To collect them, I need to run some program. That program will use registers. And so then the moment that program tries to use those registers, it will overwrite the value that is already there. So it's like standing on a floor and trying to take a photograph. You'll not be able to take because your feet will be covering a tile. Right? So somehow you'll have to hang yourself from the roof. Correct? If you want to take a photograph of the floor. So an analog of that would basically be that for any program whose job is to take a snapshot of all the registers, it needs to have other registers at its disposal, extra ones. So the register snapshotting code uses those extra registers to do its job, and with that it can take a snapshot of all the regular registers. These extra registers are called privileged registers, which only the OS code can use. Right? So this is one example that we had seen when the architecture course was being taught based on my book, that extra registers are needed. Without those registers, it is not possible to collect a snapshot of all the general purpose registers. Correct? So that part I think we remember. In addition, there are a few other hidden registers like flags. So what flags does is that it stores the result of the last comparison such that your branch instructions can now operate on the basis of flags. So that is normally not visible directly. Of course, is visible kind of implicitly because your conditional branches rely on the flags register. But if, let's say, you want to store all of its contents, it was not accessible to us. But it had to be made accessible for interrupt handlers and so on. So in this case, you sort of need some sort of a privileged mechanism to take this and store it somewhere. All right. Then you can have control registers. For instance, when my web camera is active, there is this little light beside the camera, right? That is turning on. Maybe I can turn on an LED, turn off the fan. So these are all privileged registers which are being used. I can shut down my display. So these registers are controlling parts of my laptop which only the OS should control. So that is a control register. Then of course when I'm doing debugging, let's say I'm setting breakpoints or something, where my program is running but it is being asked to stop when a certain instruction is reached. In that case, you will use a breakpoint which will use the debug register. Yeah, tell me.
Suppose we are having a very basic model of we need to activate this program which is not it needs to access the flags now because
No, it will access the flags, but that it will access by conditional branches, and the conditional branches are accessing the flags part implicitly. right? But let us say I want to store all the flags in one register, then there is no way of doing so in most ISAs. They don't have a general instruction, they have a privileged instruction, where whatever is the state of the program that is normally not completely visible to you, it is made completely visible to the OS for effective transfer and storage. All right. And then we have IO registers. So IO registers, the job is that you write something in IO register and then it gets reflected on your device. For example, you can have registers connected to your printer. You write something there, it will start printing. So all of this is the prerogative of the operating system. Using them is the prerogative of the operating system, not of anybody else. And these additional registers you will kind of find in part 2 of the instruction manual, where these are duly listed, because after all, any hardware vendor has to release specifications that need to be given to OS writers. And that is why there is always a part 2. So we'll try to find out how the hardware knows that it is actually running OS code and it is not running general purpose code. So what we will do is that we will use the notion of the current privilege level. The current privilege level in earlier processors was either it is privileged. Privileged means it can run the OS, or it is not privileged, which means it is running a regular application program. So there was a CPL bit in the hardware where CPL equal to 0 indicated it's in privileged mode, which means it's running the OS. So the program that is running, in this case the operating system, can issue privileged instructions. Whereas CPL equal to 1 indicated that it's running in application mode, which means a regular program is running, so its powers have to be curtailed. Correct. So now this has become slightly more general. So now we have rings. So rings are essentially 4 levels of privileges, not 2, not binary, but 4 levels. So ring 0 is typically the one with the highest privilege, which can be the operating system, or let's say we are running some what is called a type 0 virtualizer, type 0 hypervisor, which is basically a very thin operating system that runs other guest operating systems on top of it, then that would be running at ring 0. So whenever you boot the one with the highest privilege level. And then rings 1 and 2 are basically for virtual machines. And finally, ring 3 is for the application programs, which could either be running on the operating system in a non-virtualized environment, or could be programs running on a guest operating system in a virtualized environment. So far, so good. So this sort of gives the hardware an automatic method of finding out whether it is running in a privileged mode or non-privileged. And clearly, if it is running in a privileged mode, there are a lot of things that the running program can do which otherwise it cannot. So whenever you do a context switch, you're running a regular program, you run the OS, the privilege increases, and vice versa. So what is it that this extra privilege allows you to do? Well, so for non-privileged instructions, you are the regular instructions, that there is no issue. But let's say that when it tries to access a privileged register, let's say that a regular program attempts to shut down the system, which means there is some instruction to shut down the system, it issues that instruction. So you can't stop it from doing so, but the question is that what do you do in response? So clearly you don't want any normal program to have the power to shut down the system. So one is that you may want to generate an exception and terminate the program saying that you violated your access rights and you are not allowed to issue this instruction, but you did. Not allowed. This is one option. The other is that there is some effect. Okay. There is some effect in the sense maybe a response comes back with some error code. Or let's say that with shutdown, maybe something else happened, somewhere an entry is made that an attempt was made to shut down. So this is something with some effect. And there is no effect at all. That's the third option, where the hardware treats it as a no-op, which means that as if this instruction was never issued. So we will see when we are designing virtual machines that the first one is fine, the second one is fine, but if there is some effect, it signals a massive problem. The reason being, as we shall see, that this is acting like a polymorphic instruction. Polymorphic basically means it has some effect when it is run in privileged mode and a different effect when it is run in non-privileged mode, and that effect is not an exception. So what happens is identifying such instructions and dealing with them actually becomes very tough, which is one of the single largest problems that virtual machine writers face, mainly because they have to deal with such instructions. Why are such instructions there? They are there because when the instruction set designers were doing their job, they were not able to think that far. Right? So virtual machines are a recent phenomenon. Right? Even way back when I was doing my PhD studies, virtual machines were not common. They became more common after 2008, 9, 10, after the advent of cloud computing. But instruction sets were designed in the late 70s. And then, of course, it was a continuous process, but mainly late 70s, 80s, and so on. So clearly, then, this realization had not dawned upon designers that one day the operating system itself will be run like an application, the way you do using VMware or VirtualBox or KVM or something. This foresight was not there. So clearly they cannot be blamed, because whatever we do today, we don't have the foresight of what's going to happen tomorrow. Privileged instructions, on the other hand, which is like the part 2 of the instruction manual, they can access all registers. Exceptions are normally not generated unless you do something which is otherwise not allowed. So the OS and other OS-like software, like the virtual machine managers and so on, which are essentially thin OSs, they can access privileged registers, issue privileged instructions, and do things like, let's say, shutting off the fan, turning on the fan, shutting off the display. These are all privileged actions. So now let's talk about how an OS and a regular program actually communicate. There are several mechanisms. There are interrupts, exceptions, and system calls. So an interrupt is an externally generated event. So an interrupt is when you move the mouse, or you press a key on a keyboard, or a packet arrives via the network card. That is an interrupt. In this case, what happens is that essentially it's like one of you trying to ask a question. What would you do? You would like to raise your hand. So raising your hand is like an interrupt. The fact that I am taking cognizance of your raised hand basically means that I am the CPU and I am acknowledging the fact that you have raised an interrupt. So then I will pause what I am saying, right? But I'll remember where I was. Otherwise, how will I restart my conversation? That is like saving the context. Then I'll ask you to ask your question. I will answer it, which is servicing the interrupt. And then I will resume at where I had stopped. Same point in the same slide. This is restoring the context. So the OS would do exactly the same. The moment you bring anything to the OS's attention, you meaning hardware devices, what will happen is that the context of the running program, which is its runtime state, will be stored. Then the interrupt will be serviced. Then the OS can do lots and lots of other work, including running other programs. Finally, when it finds the opportune moment, it will run the program that was paused and resume it at exactly the same point, unbeknownst to the program that was paused. And this pausing and resuming can happen millions of times in the life cycle of a program. It should not have any effect at all on its correctness. All right. So this is interrupts. An exception is slightly different, even though the processing pathway is mostly the same. An interrupt is when a hardware device is trying to bring something to the OS's attention. An exception is when your program does something wrong, like division by zero. One of those classic segmentation faults that all of you have seen, where you try to access an illegal address and that address is often zero. So that is when an exception is generated. Then there is a need to suspend the program and take a look at the exception. Then the OS often decides to terminate the program, but this is not mandatory, right? So let us say that you issued some instruction which is not supported by your processor, but let's say that you issued the square root instruction and square root is not there in your processor. Then what the OS can do is that it can simulate the square root operation. It can take the number and compute its square root. All of you would have studied the square root algorithm in class 7 or 8, right? Where you take 2 digits at a time, and correct? So you would have done that. And so it can always compute the square root using divisions, multiplications, adds and subtractions. Compute an approximate square root, or well, it can be made as exact as the precision, and then you can insert it in the register and return it back. So in this case, even though an exception is generated, the program is not terminated. So not all exceptions lead to program terminations. Right, so later on we'll see there's something called a page fault, and that does not lead to termination. So basically all kinds of exceptions are not bad. Then we come at system calls. So the main idea is that how do you invoke an OS function? Because clearly doing something with hardware, like sending a network packet, receiving a packet, or let's say getting something from the hard disk, so that requires OS intervention, and you clearly cannot make a function call. They are not in the same address space, so a function call cannot be made. And the OS is obviously not running because it's a program, and since you are running, the OS is not running. At the moment, only one program can be running on a core. So what you do is that you raise a dummy exception, a fake exception, which will still raise the, tell the OS, raise the attention of the OS, and that will lead again to the same set of steps. It will lead to a suspension of the program's execution, storage of the runtime state, and then you can pass data to the OS such that, so obviously you'll pass data via registers or memory. It will service your system call. So if your system call was to read a certain file, then essentially it will read the file, it will give the data back to you. And once the data comes back to you, then the program is ready to run because the system call has returned. And so then you resume the program at exactly the same point of time, and wherever it was expecting the return value, it will get the return value. So far so good. So question. An interrupt is generated by hardware to essentially grab the CPU's attention. For instance, if let's say you click a key on a keyboard, then that hardware is the keyboard and the interrupt has to be serviced. A system call is when I as a program need some OS help. Let's say I want to read a certain file. I do not have adequate privileges to read a file. Correct? Or let's say I want to send a message to my friend over the internet. So I do not have adequate privileges to access the network card. That is when I need the attention of the OS. So if I need the attention of the OS, the only way to do so is by the interrupt mechanism, which is why I generate a fake interrupt. There is no other way of bringing anything to the attention of the OS.
Sir, with the system call, generate
Yeah, the moment the OS finishes its job, it needs to go back. Right. So the question is that once the OS comes in, it does its job, and wherever it is asked to place the results of the system call, it does so. Then the question is OS now has to recede, right? So OS has to go out of the picture and it has to load the original process. Well, so basically it will restore the state. Restoring the state is tantamount to loading it, because you will set the program counter to its next program counter of that process. Setting the program counter to some value is tantamount to actually suspending yourself and running the other process. Right? So just by overwriting the program counter, which the OS can, via different instructions, it is tantamount to suspending yourself and running the other process. Of course, also a mode change has to happen. The OS is privilege mode, so from privilege you'll have to go to non-privilege. That is why most ISAs have an IRET, interrupt return instruction, or a sysret, system call return instruction, where you actually go back to you overwrite the program counter with a mode switch. That is what you do. All right, that answers your question.
So you also talk about signals.
Yeah, signal is a separate issue. We will not talk about signals here. We will talk about signals in chapter 4. A signal is basically like this, that if let's say I move the mouse, so finally, and your application is paint. If I'm moving the mouse, it is painting a line on the screen. So the fact that I'm moving the mouse means that the mouse is generating an interrupt. That interrupt is coming to the OS, and the OS is being told that you are at point XY. From XY, you have moved to X dash Y dash. This information is now there with the OS, but the fact is it is not there with the process. So the process has to be informed that the mouse was at XY. From XY, it has gone to X dash Y dash. You kindly do whatever you want to do. So there has to be a back path from the OS to the process. That mechanism is called a signal. And signal is clearly asynchronous in the sense that you are not waiting to receive it, because you don't know when the user will move the mouse. So it is kind of a reverse path where the process is notified of some sort of a hardware event via a signal through the OS.
So can we generalize that a hardware generated interrupt will always come before a system call?
Well, a system call generates an interrupt. A system call's job. So what happens is that even user programs do not directly make system calls. So what happens is that if you have a user program, then it actually calls a library call like your C library. A library is nothing but a set of functions. The function wraps the system call in the sense it takes your arguments and places them at exactly those locations at which the system call expects the arguments. Then a system call is made, which is equivalent to generating an interrupt, and interrupts are of course hardware interrupts, and then the OS comes into play. And needless to say, the first step is to store the state of the running program, and then you process the system call, figure out what the return values should be, place them at the right place, and then you resume the stalled original process. Does that make sense? So interrupts, exceptions, and system calls are interrupting mechanisms because they are directed towards the OS. Signals are the only mechanism which are directed away from the OS. They are from an OS to a process, right? So that is the difference. So if I were to maybe draw it this way, if this is the OS, so you have interrupts which are generated by hardware devices. You have exceptions. The exception is essentially generated by the program, but program does something wrong and then the CPU generates an exception. And then you have system calls which are again generated by the program. But in this case, what happens is that you have a system call instruction where the program tells the CPU to kindly generate a fake interrupt called a system call on its behalf. Then we have signals, where the center of gravity is the program itself, is the process, right? So I'm using the word program to kind of make life easy for you. It should be technically it should be the process. So a signal comes, sorry, did I do something? Yeah. So in this case, the process lies here and the signal comes from the OS. So in this case, the direction of transfer is different. So let us look at how a system call is generated. That will clarify many of these doubts. So there is a little bit of a change here. This is actually 548 now, and kindly look at the latest version of the slides. So there is something called syscall 64 .tbl that has the data, but so this link is not correct. The UNI STD link is not correct, but the latest version of the slides has the correct link. And so there is a system called table. So the current version, actually the version we are following, roughly 6.2 of the kernel, that has 548 system calls defined. That's a lot of system calls. And the way that you actually invoke a system call is very simple, very easy. You move the system call to the RAX register. I'm talking of 64-bit x86. So you move the system call number. So the way that you specify the immediate is with a dollar. So let's say the system call number is 17. So you move 17 to the RAX register. So in this variant of x86 64 assembly called the AT&T format, the destination is at the end. This is quite unlike simple RISC and RISC-V, where the destination is at the beginning. So in this case, the destination is at the end. So what happens is that your system call number goes to RAX, and then you simply do the syscall instruction, invoke the syscall instruction. The syscall instruction, what it does is that it generates an interrupt. You go to the OS sees and observes that a system call has happened. It stores the state and it first looks at the contents of the RAX register to find the system call number. In this case, the number is 17. It will then go to a system call table. It will go to number 17. Alright, it will go to number 17. In number 17, you will have a function pointer. Okay, the function pointer will point to a function, and then that function will start executing to service the system call. Of course, before going here, the state will be stored. So I'm always assuming that the default action is to first store the state of the running program. So you do all of that, you kind of come to a clean point, and then you start executing. So then from the stored state, you extract the number of the system call from the RAX register, and then you go to a table. The table has a function pointer. What is a function pointer? It is a pointer. A pointer is an address. If it's a 32-bit system, it's a 32-bit address. If it's a 64-bit system, it's a 64-bit address. It is a memory, a pointer is a memory address. And in this case, a function pointer it points to the first byte so it points to the first byte of the function's code. So the point at which you start executing the function, it points to that point. Alright. So kindly look up how to define function pointers in C. So this is kind of the homework for today, because we'll be using this extensively in Linux. So what I would suggest is all of you write a C program where you define a function pointer, correct? And then use it. So you will see that function pointers are a great mechanism because they allow you to call different functions based on data. It connects data with code. So function pointers are a very strong mechanism, and they also require fundamental modifications to the instruction set, because they kind of connect the which function you will call to the value of a data. So you can put the data in an if statement and say that you look, if this is this, the function pointer points to this function, so on and so forth. Like in this case, if the data is 17, then just call the function pointer of the system call corresponding to the number 17. What is a function pointer? That I told you, it's an address and it points to the first byte of the function's code. How do you use it in C? That is your homework for today. So you write a program in C with function pointers and make it run. Alright. So the syscall instruction is essentially the interrupt generating instruction.
Are the system calls defined in the table individual function?
They are. You look at the table. So the table basically says that for this, the table and so it's just not the table. If you see that directory, you'll find the table as well as a bunch of header files as well. So they say that this is the function for this system call number. So if this system call comes, this is the function that you invoke. All the functions have a standard call pattern, standard set of arguments. Otherwise, it will make life kind of tough. So they have the standard set of arguments, same set of arguments. Alright.
How do we pass the arguments, because the RH register contains the...
Yeah, we will look at it in detail in chapter 4. So other registers hold the arguments. So in many variants, you can have 6 additional registers or maybe 5 additional registers for holding the arguments. And the rest of, if there is more data, it has to be passed. You'll have to give a pointer to where all of that data is in the user process's memory. Then the pointer is passed and the kernel has to read it from there. So along with syscall, there is another mechanism, which is an older mechanism. It's not used, but it will still work, which is that you do an interrupt directly. So the int function, the int instruction generates an interrupt directly, right, without any pretense of a system call. So whatever interrupt number you will give, every interrupt has a unique number, similar to every system call having a unique number. Whatever number you will give, it will just create an interrupt with that number. So in this case, it is 0x80, which is 128 in decimal. It is 0x80 in hexadecimal, and that is what you get. If you can generate an interrupt absolutely directly. That used to be the method before the syscall instruction came about. Is that clear? So essentially all are handled in the same manner, where the idea is to knock on the doors of the OS to draw its attention, right? You raise your hand to draw or grab its attention. So the thing is, either you rely on a hardware interrupt, can be done, or what you can do is that you can automatically generate an hardware interrupt, right? So the CPU can use this as a pretext to invoke an OS routine. or every fault or exception, again that's an interrupt. So every fault or exception will have an exception number. And the processing pipeline is the same. You store the state, look at the number, based on the number and the type. Because the type is important, right? The system call is a different type, interrupt is a different type. But finally, every system call will have a system call handler, every interrupt will have an interrupt handler, and every exception will have an exception handler. And all of that will happen via tables of function pointers, where the number indexes the table and the output is a function pointer which is used. So you use the function pointer and you invoke that function. Okay? And so that is why function pointers are very important, which is why you need to take a look at it. So this is, in a sense, if you look at all of these mechanisms, it's an unconventional and weird way of drawing the OS's attention, because there is no direct method. It's not like you write something somewhere or you call a function. It's not like that. It is genuinely an emergency mechanism via which you invoke the operating system. The standard analogy is that if you want to draw the attention of the fire station, you set your house on fire. Right? So pretty much it's like that drawing the attention of the OS is difficult. You have to go only by this expensive interrupt processing route. That is why whenever you are writing any program, you minimize the number of system calls. Right? So that is why the moral of the story is that whenever you are doing any program, writing any program, you minimize the number of times you have to go to the OS. Because the more you go, this is a heavyweight mechanism. It's not a lightweight mechanism. That is why normally what people do is that they do what is called batching, and the C library also does that. Instead of writing, let's say, small chunks of data to a file, like 4 bytes at a time, it is a much better idea to do what?
Restore the output at some point.
Yeah, let's say do it at maybe 4 KB at a time. Write to that memory buffer of 4 KB, and then when you are writing to a file, write the 4 KB in one go. And 4 KB is good because it's the size of a page. So write all of that in one go, or even at a larger granularity, such that your system call overhead is minimized. Right? So the dead weight, which is associated with saving the state, restoring the state, all of that is effectively minimized. So far so good? Alright, so we have looked at the main mechanisms. So what does the CPU basically do? So the CPU, as we have seen, saves the state of the executing process. This state is known as the context. Alright, so the context is stored, then the interrupt handler is loaded, or the system call handler or the exception handler, but many a time all three are referred to as interrupts because they are interrupts. So this has to be figured out from the context, and this is done via a table and indexing mechanism where the table stores function pointers, and then you figure out what needs to be done, and finally you resume. So the saving process, if I were to look at it in some more detail, I would store the privileged registers, the state, as I would like to store the state of everything, right? Whatever my process has touched, I would like to store all of it because that is the process's runtime state. It is a part of the context. So you will have your registers. So registers will be your regular general purpose registers as well as the flags and the special purpose registers like ALU flags and so on. This is the register state. Along with that, I will have my memory, which are all my memory contents. The memory, it turns out you don't have to save and restore because the built-in virtual memory mechanism takes care of it. So this, there is no need. So we shall look at this later, but essentially there is no need to save and restore it, because in any case another process cannot tamper with it. But registers are a separate issue, because registers are the same and they are shared across processes. So that is why this is important. The next is the program counter, which is where should I resume from. Correct. This is kind of tricky. This is not very straightforward. The reason being that, let's say in many cases, for example, a page fault. A page fault, as we shall see later, is where there is some issue in getting the data for the address because it is not there in memory right now. It's the address is valid, everything is valid, but the data at the moment is not close to you. It has to be brought close to you, then only you can access it. In that case, there is a need to reissue the same instruction again. In this case, the PC is nothing but the PC of the faulting instruction. In the case of a hardware interrupt or system call, it should actually be next PC, right, where the current instruction executed correctly, and you will resume it at the point of the next PC. Right? The current one will not be re-executed. In that case, the next PC could either be the current PC plus 4 if every instruction is 4 bytes, or it could actually be the branch target. Which basically means that, maybe the current instruction is a branch and is branching somewhere else. So that somewhere else is the branch target. So this could be the branch target. So the next PC, as I said, could be the one that just follows it in the program, or it could be the target of the branch. Regardless of what it is, both are the next PC. Now, whether you will resume from the PC or the next PC depends upon the type of the interrupt that was generated. In some cases, the same instruction has to be executed again. In some cases, the next instruction has to be executed. All right. So basically the state that has to be stored is this much and this much. So this comprises the program state, and the memory does not have to be stored and restored, as we shall see. So all of this comprises the context which has to be stored somewhere. Somewhere basically means in the OSS memory. So the moment that there is a context switch, the operating system, the kernel code, the kernel is basically the core part of the operating system, whose job is to manage all the major aspects of related to memory and processes and scheduling and so on. Right? Also the interface for the drivers, but the drivers are not a part of the kernel. So drivers are always treated separate. The memory remains untouched, so we need not worry about that. And the PCs of this instruction, so as I said, can be PC or next PC. And we have to restart the process from exactly the same point. So I just simplified the text a little bit, but as you can see, there is more nuance to this PC, because many times re-executing the same instruction is required, and many times it's also not required. But in any case, your point of resumption is what is stored in the context. Because when you restore the context, what your processor will do is that it will jump to the point of resumption and start executing from there. Which means that now the OS has been suspended, it's not running, and the original process is running. So the original process should never get to know that all of this is happening. Of course, it can do more fine-grained measurements like look at the timing and so on. But in general, it should never get to know that this is happening maybe millions of times in its lifetime. It should be absolutely seamless.
Will the address space of the process and the OS be same?
Obviously not. The address space of the process or any two processes or the process and the OS are never the same. The address space, we will define the address space in more detail. We haven't encountered the term address space up till now. So we will see what the address space is in chapter 6, where we will look at it, but whatever you think it means, it is separate. It can never, otherwise there will be a massive security issue. So the life cycle of a process is henceforth is basically very simple, where you execute, then there is a context switch, the operating system runs. The moment the control goes to the OS kernel, there is no guarantee that you will come back to the process, right? There is no guarantee. So it is possible that some other process may start to run, but ultimately you'll come back to the original process. So you'll again restart execution. Again, you may be interrupted. Again, the OS may run. The OS may run its own processes. It may run other user processes. And then you'll basically keep coming in and keep going out. So the process should have no way of knowing that it is being what is called swapped in and swapped out. So when it's running on a core, you say it is swapped in, and when it is not running, you say it is swapped out. So it should be oblivious or agnostic to so many context switches that are happening. So how does the OS see a process? So there is another point here which needs to be elaborated, which is that the OS looks at the process as basically a suitcase where its entire context is packed inside it. It's like a bag. So if it is, let's say, running on this CPU, it can get swapped out. But when it is swapped in, there is no necessity for it to be swapped in on the same CPU in which it was running. Even though it is desirable, because then the caches will be warm, so it will find the data close to it and so on. But there is no necessity that it should be swapped into the same CPU. It can be brought into a different CPU. That is because its entire runtime, as I said, the memory is not being saved and restored. That is automatically being taken care of. You're basically looking at the program counter and the register state. That can be put in this bag called the context, and you can safely store it, and you can safely resume the process by bringing its context to a different core and starting it there. It should make no difference at all. And if you actually see, if you run the Linux stop command, you'll actually see your processes jumping around cores all the time. No issue.
Exactly. We need to see it.
So OS has scheduling algorithms where there is a notion of efficiency, and in general you would of course want processes to remain in a runtime state, but then the point is that you may have few cores and too many processes, then there has to be switching. Also, a process may go to sleep because it is waiting for some hard disk IO request, right? And in that, till the data comes, it has nothing to do. And maybe when the data has come, a high priority process is running on its erstwhile CPU. So that is why processes, I am kind of loosely conflating the term CPU and the core here and a core here. They are not the same, but let's say for our discussion they are. So if it basically gets swapped out from here on any core, it can start running. Because whatever it needs to start running, that I have correctly stored in my context. So I don't have to worry or bother.
We are talking about caching like separately for
Yes. So that's all right. As I said, caches are part of the memory system. Memory I don't have to bother, because the virtual memory system and cache coherence will take care of everything. So memory is not a matter of concern. It's only the register state. And if I count the program counter also as a register, then it's only the register state that matters. That is for performance. That is not for correctness. So you always try to ensure that if I was running on a same core, then the first priority should be given to that core. That is because some of my data will be there in its caches. So what is said, its caches will be warm for me. But the point is that it's like this, right? Let's say you frequently go from Delhi to Bombay. And in Bombay, a certain car company takes care of your travel. Now, if I give you a choice, you will prefer that same cab company. That is because you know the company, you know its management, you know its drivers. So the same way, if you are running on some CPU, some of your data will still be there in its caches. The caches will be warm for you. So you would prefer that, but there's no guarantee that you'll always get your preference, right? Because processes have their priorities. So there is absolutely no guarantee. Then if another CPU is available, you go there.
So, when OS is running on one code, then all the will also like that.
All the other cores will be working, all the cores are independent. All the cores have their program counters, all the cores independently run a process each, and they are absolutely independent. So they are fully independent pipelines. There is no notion of coordination between them. You can think, if let's say if a multi-core CPU has 8 cores, it is running 8 separate programs. Think of it that way. Of course, there are coordination mechanisms via memory and cache coherence and so on, but that is only for getting the state. They are running 8 different programs, and if the 8 different programs are non-OS programs, the OS is not running, and something which is not running cannot act.
So, can you run on multiple codes?
Well, then it would be separate OS processes running on. So there is nothing called the OS. The OS is fine for people outside this course. Inside this course, on one core, one process is running. It's a single threaded process which is running on one core. So let's say there are 8 cores and 3 out of them are running OS processes. That's perfectly fine. But there are 3 different processes. Correct. And they are doing different jobs. So the OS would treat it as a suitcase. Things can be suspended and resumed and moved around all the time. And as I said, there are 2 kinds of processes, user processes and OS processes. And if you see your list, if you do a Control Alt Delete on Windows or a top on Linux, PS-EF on Linux, then you can see all the processes. And the processes will have different privilege levels. Some with an OS privilege, some with a user privilege. Regardless of the type of the process, user or OS, it is important to note that each core runs a single process at a time, which could either be a user process or could be an OS process, but it never runs both at a time. So this ends the current lecture at this point. So we will talk more about how this process scheduling happens, how you kind of swap out a process, which means we pause it and kind of remove it from a core, and how we bring in a new process. We'll discuss more about such mechanisms in the next lecture, which would basically be the second lecture of the second chapter. This was the first one. So see you in the second lecture.